Instead of learning from static examples, imagine an agent discovering optimal strategies purely through trial and error, interacting with an environment, facing consequences, and refining its actions over millions of simulations. This isn't about fitting a curve or classifying an image. Reinforcement learning is a paradigm where an agent learns to perform a task by maximizing a cumulative reward signal over time within a dynamic environment. Think of it as experiential learning for algorithms. The core loop involves observing the state of the environment, taking an action, receiving a reward or penalty, and transitioning to a new state. The agent's goal is to learn a policy, a mapping from states to actions, that guarantees the highest long-term reward. Algorithms like Q-learning or proximal policy optimization (PPO) iteratively update value functions or directly refine policies, navigating the complex trade-off between exploration and exploitation. Consider autonomous drone navigation through a cluttered forest. A human cannot handcode every possible collision avoidance rule. Instead, an RL agent trained in a simulated environment can learn to identify subtle air currents and obstacle configurations, adjusting its flight path in real time, far exceeding hard-coded heuristics. Unlike supervised learning, which requires vast labeled datasets, RL thrives where explicit labels are scarce or impossible to generate, where the optimal path emerges only through sequential decision-making. Compared to traditional control theory, RL offers unparalleled adaptability to unforeseen changes, learning dynamic models directly from interaction, without prior system identification. A lesser-known implication is the integration of model-based RL with generative models. Agents are not just learning policies, but also building predictive internal models of their environment. This allows for imagination and planning ahead, dramatically improving sample efficiency. A crucial bottleneck for real-world RL deployment in robotics and complex control systems using Python frameworks like Ray-RLib. Reinforcement learning challenges our conventional notions of intelligence. It demonstrates that true mastery can emerge not from explicit instruction, but from persistent iterative engagement with complexity, a testament to the power of self-discovery in algorithmic design.